Excellent. So yeah, it's just gone 2, so we can start. So yeah, welcome back to everyone for this new semester of the Applied and Computational Maths seminar series. So yeah, it's a pleasure to welcome Simone and Michele from the University of Plymouth today. Simone started his academic career in Italy before coming to the UK on a Royal Society grant, and yeah, he's now at the Civil Engineering Department in Plymouth as a lecturer. So yeah, he's going to tell us today some of his modeling with the oceans, but this time specifically at the bed of the ocean and these thermal boundary layers where we get coupling between flow and thermal effects. So excellent. Over to you,
Okay. Hi, nice to meet you. So first, I would like to thank Usama and Tom for the invitation. So it's always nice to present your research to other researchers, academics, or PhD students. So thanks for the invitation and thanks for the lunch as well. So today you will see basically this. So some the effects of free surface waves on the thermal boundary layer located at the seabed. Now, like Tom said, currently I'm based at the University of Plymouth. I'm a lecturer in civil engineering, and my research is mostly focused on theoretical modeling of fluid structure interaction phenomena with application to wave energy converters. I analyzed this Ginzburg-Landau evolution equation for the trapped mode amplitude. I analyzed chaos behavior by applying some linear dynamical system theory. Then I analyzed the behavior of a flexible plate in the ocean, excited by free surface waves. And I also investigated the propagation of acoustic gravity waves in presence of sound speed vertical profiles, and Usama is a great aspect in this field. Then I recently published a paper on the hydrodynamics of weakly nonlinear dispersive waves with application to landslide tsunamis. And also I collaborated with Professor May from MIT about this problem, so the REBOA, which concerns the dynamics of elastic balloons used for surgical procedures. And more recently, I started working on this problem, so heat transfer related with ocean waves. Now, there are really very few studies that focus on the effects of free surface waves on heat transfer in the oceanic environment. So my idea is to, in order to study this effect from free surface waves, is to develop a model based on this equation here, which is the convection-diffusion equation or transport diffusion equation. So this is linearized, so there are no linear terms here. So it looks simple, but if U and W, which are the velocity components, if these components are complicated, well, the solution can be challenging. Now, in this case, T is the temperature, T is time, small t is time, then X, Z are the coordinates. This key here is the thermometric conductivity, and the U and W are respectively the horizontal and vertical velocity components. Now, the application of this theory, maybe it can be broad. So the aim is to provide a better understanding of heat dynamics related to seawater air conditioning systems. I'm involved in this EuroSWAC project, so which is an Interreg project. Here you can see a sketch. So basically, here there is an intake pipe and outtake pipe to use seawater as a refrigerant to air cooling. So, for example, here it could be interesting the temperature field around the outtake pipe. Then another application concerns the biofouling of microorganisms around structures, because biofouling can be affected by temperature. Then underwater data centers, coral reefs, and also satellite data calibration, because satellite can basically understand the characteristics of the ocean on the upper layer. So again, this is the governing equation for the temperature T. I'm considering laminar flow, and I consider also flat heat sources located at the seabed for simplicity. So that means that large gradient of temperatures occurs in this boundary layer, viscous and thermal boundary layer. So that means that the velocity field must depend on fluid viscosity. So in water wave theory applied to boundary layer, viscous boundary layer, we usually assume these following scales. So K is the wave number, so it's 2 pi divided by the wavelength. This delta here is the thickness of the boundary layer, which is defined in this way. So it's the square root of 2 nu divided by omega. Nu is the kinematic viscosity, and omega is the frequency of the free surface waves. A is the amplitude of free surface waves. And this is the scale for time. So here you can also see the scale for the horizontal and vertical oscillations in the region close to the seabed. Okay, so these are quite popular scales in the field of viscous boundary layer in the ocean. So if we use this and substitute these scales into the continuity and Navier-Stokes equations, we get the following expressions here. So continuity remains the same. This is the Navier-Stokes component with respect to the horizontal coordinates. Here, this term here, as you can see, shows that the pressure depends just hydrostatically. So it can be written in this form. So it varies accordingly rho gz. So that means that the horizontal variation of the pressure has the same, follow the same variation of the pressure outside the boundary layer, so in the irrotational field. So that means that we can combine these two equations here, and we can get this expression here at the bottom. So this term here, this big U term, is the outer velocity. So it's the velocity related with the free surface waves close to the seabed. Okay. Now U can be written in this form. So U0 is the spatial component, and the term here, the second term, represents the oscillations, so the time dependence, and R8 is the real part of this term. So we can use this and apply a perturbation expansion. Okay. So again, this is a standard procedure used to analyze seabed mass transfer phenomena in the ocean. Okay. Now, U1 are the leading order velocity components, U2 are the second order components. So here we are developing a second order theory. Epsilon represents the wave stiffness. So in this theory, we could, yes.
Sorry, did you assume shallow water?
No, we are in the case of intermediate waters. So it's general. Okay. So we are just assuming that AK is much smaller than 1. So the wave stiffness is smaller than 1.
Yeah, the water depth is not in this problem, is it?
No, it's general.
Oh, it was the beginning with KH, right? Or...
No. We are not shallow water. So it's completely general. So these are the scales that we usually have even in intermediate water depths.
Yes.
So AW is basically the velocity, is the scale for the water particle velocity on the free surface. So the presence of sign, the hyperbolic sign, it's the effect of water depth. So, but we are in the intermediate waters.
It has to be intermediate, right? Otherwise,
yeah, exactly.
If it's deep water, then you don't have any effect.
Exactly. So, okay. So we apply this perturbation approach, and we have this first equation here, so which is a kind of a heat diffusion equation forced by this term. Okay, so which is the effect of free surface waves at the seabed. Okay. Now, we apply these two boundary conditions. So we have the velocity equal to 0, so the no-slip condition at the seabed. And we also assume that the velocity in the viscous boundary layer matches the outer velocity, so the velocity of the related with the free surface waves. Now, this expression here can be easily solved. And here you can see the two solutions. So once we get U1 first, so the horizontal component. W, it can be found by applying the continuity equation. Okay? So, and these velocity components, they are related with a synchronous response. So they have the same frequency of the incident waves. Now, we can move at second order. So this is the first order solution, okay, of the velocity field in the viscous boundary layer. The second order problem, in order to find the second order problem, we need to solve this expression here. Now, we need to find U2. Now, on the right-hand side, we have quadratic products, okay, of U1 and the rotational velocity field. So when we multiply this component, we have a second harmonic component and the drift, or the time-independent velocity component. Now, the second harmonic component, it gives very small contribution, so it's not considered here in this study. But the time-independent component, or the Eulerian mean flow, it plays a significant role. Okay? This is well known, for example, in mass transfer at the seabed. So we focus now just on the Eulerian mean flow component. We can average this expression here, and we can get this differential equation. Now, the boundary condition that we apply are shown here. So we have again the no-slip condition at the seabed, so in z equal to 0, and we apply the non-tangential stress at very large distances. Okay. We can solve this expression, so we just need to integrate with respect z, and we can get now the expression for U2, so the horizontal component, and the vertical component of the Eulerian mean current. Now, as you can see, that depends on these variables, U0, and the derivative of U0 with respect to x. Inside these expressions, you can see F1. So this function is shown here. It's quite complex, but it represents a combination of oscillation and hyperbolic functions. And the asterisk denotes the complex conjugate of the relevant variable. Now, basically here, we need to just substitute a suitable expression for the velocity potential. We need to assign this irrotational velocity component. So, for example, since we are considering a two-dimensional geometry and a flat seabed, we can consider the following velocity potential for free surface waves. This is the velocity potential for propagating and reflected waves. So when r is equal to 0, we have just propagating waves. When r is equal to 1, we have the effects of reflected waves. So this is basically, when r is equal to 1, we have basically the dynamics in front of a breakwater. We have standing waves, okay? And k, which is the wave number, it can be found by solving this dispersion relation, which relates frequency and wavelength. And this is valid in intermediate waters, okay? For any value of k. Now, we are assigning this velocity potential, so we can now find U0. So the velocity in the irrotational domain. And this is given here, because the horizontal velocity is simply the derivative with respect to x of the velocity potential. So the expression for U0 is given here. Now we can substitute this U0 inside the previous expressions for U1 and U2, W1 and W2, and we can get these very long expressions for the velocity components. So basically, these velocity components represent the velocity components in the viscous boundary layer at the seabed. Okay. Here you can see the first harmonic response at the leading order. The second term represents the Eulerian mean flow. Okay. It's interesting to note that the velocity component here, so the Eulerian mean flow, the vertical component of the Eulerian mean flow is equal to 0 in the case of simple propagating waves. Okay. So when we have simple propagating waves, the component is simply horizontal. So the flow is simply horizontal. I mean, the Eulerian mean flow. Okay. As you can see, if we substitute these quantities into the formal equation for temperature, well, the solution can be quite challenging because this is quite complicated. Now, we need to understand what's the range of application of this theory. So we are considering laminar flows, okay, not turbulence. Now, some authors analyze the stability of laminar flows at the seabed. For example, Johnson, Blondeau, Vittori, and Verzico, for example, they found that there could be some disturbed laminar regimes in this region, in this range of value of RE delta. So where RE delta is the Reynolds number in the boundary layer. Okay? So when this RE delta is between 100 and 500, we can have some perturbation of the laminar flow. Okay? Similarly, Jensen defined a different Reynolds number, which is related with RE delta, okay, and found that when RE is equal to 10 to 5, we can have turbulence. Okay, so in other words, for example, if you consider free surface waves of wave having amplitude about having amplitude of 0.25 meters, propagating over sea depth of 5 meters, and having frequency of 1.5 radian per second, which is a common situation that we can have in the ocean. Well, in this case, RE delta is at 248, and RE is 3 times 10 to 4. So, for example, in this case, laminar flow is likely to occur. We can also decrease the frequency. The Reynolds number increases slightly, but still we have stability of laminar flow. Okay? So what does it mean? It means that at some point, when the frequency is too small, we are increasing the velocity, okay, at the seabed. And at some point, laminar flow is not possible anymore. Or if we increase the amplitude of free surface waves, okay? Because remember, the scale for the velocity depends on A and omega. So the wave amplitude and on the frequency. In this figure, I show the two criteria. So this is the criteria derived by Johnson, Blondeau, Verzico, and others. This is the criteria derived by Jensen. So here I have the free surface elevation amplitude, A, versus wave frequency for different water depths, corresponding to the different thresholds. Now, for a given value of water depth H, the laminar flow is stable, provided A and omega are located to the right of the relevant curve. What does it mean? For example, if I consider water depth about 5 meters and wave frequency of 1 radian per second, I have a stable laminar flow only if the wave amplitude is less than 0.28 centimeters. Okay? So in other words, I need to pick some values of A and omega. So my theory is valid only if I pick some values of A and omega located on the right-hand side of the relevant curve. Okay? Above this curve, we can have turbulence. Okay? Now, we need still to simplify the problem. Okay? So we need to estimate the boundary layer thickness, the thermal boundary layer thickness. That's because the viscous boundary layer thickness, defined here, the scale for the boundary layer thickness, differs from the thermal boundary layer thickness. It's different. Okay, one deals with viscosity, the other deals with temperature. Now, an estimate of delta T of the thickness for the thermal bonded layer can be found in this way. So for example, we can consider this simplified problem here. We still have a convection diffusion temperature in absence of vertical velocity component. So we are just considering horizontal flows, right? So we are trying to simulate the effects of simple propagating waves. U, the velocity here, can be written in this form as a composition of steady and oscillating components. Okay, like if you have an Eulerian, like if we have an Eulerian mean component and an oscillating component. The diffusion term related with the horizontal diffusion term can be neglected, right? Because it's much smaller than this one. It can be shown later. So I'm just reporting the dominant terms here. And at the seabed, I can consider this heat source here. So delta T is the temperature of the heat source. And this heat source is located between x equal to minus L and L. H is the Heaviside step function, okay? Here, the temperature is 0. Here, it's 0. And the temperature is also 0 at very large distances from the heat source. Okay, if I consider this problem here, this problem can be solved by using the following coordinate. Okay, so I can integrate the velocity. I can get this new variable here S. If I substitute this quantity here in the previous problem, I can simplify the previous equation, right? So I don't have the convective term anymore. But I have a more complicated term here at the seabed, okay? But anyway, the problem is much simpler. I can solve this problem, for example, by applying the sine Fourier transform here, because I have a Dirichlet boundary condition here at the seabed. And then I can integrate with respect time. So the solution of this problem is written here. It has been derived by Pedley, I think 50 years ago. So this is the solution expressed in integral form, okay? So this is the solution for the temperature. Now, U0 and the UE, so my two velocity components, the steady component and the oscillating component, can be also written in this way, right? So this represents the solution in present absence of oscillating velocity, okay? Now, if I assume these quantities here, I can try to represent the propagation of temperature. Now, I consider these parameters here. So wave, free surface wave amplitude about 0.25 meters, water depth about 5 meters, frequency of 1 radian per second. So these are the corresponding velocity. So this is the velocity that I would have at the leading order. This is the velocity of the Eulerian mean flow. As you can see, the Eulerian mean flow component is much smaller than the leading order velocity. But as I will show you later, this is the main actor in influencing the temperature diffusion. And I have these two Reynolds number. So I assume that the laminar flow is stable. Okay, so I have this heat source here from -2 to 2 meters. So I have the oscillating component and the Eulerian streaming, the Eulerian mean flow, right, directed rightwards. As you can see, there are fast oscillations, but the temperature feed, so this is the temperature, bends towards the right. So here the heat source has temperature of 10 degrees, okay? Now, for simplicity, I neglect the effect of the fast oscillations, okay? So what's going to happen? So the temperature tends to propagate upwards and then bends towards the right, okay? So here you can see time, so 300 of seconds, then up to 500. Okay, now I compare now this picture with the previous one when time is equal to 500 of seconds. And I get this. As you can see, the thermal boundary layer thickness is not affected by fast fluid oscillations, right? So this thickness here is basically the same that we have here, okay? So that means that to estimate the boundary layer thickness, we can simply consider the Eulerian mean flow, okay, directed horizontally, for these scales of the heat source, okay? So if the heat source is not very, very small. Now, we can try to simplify the problem for the temperature, okay? So we just go back to the equation for temperature and assume now these two following scales. Delta T is the thickness of the thermal boundary layer, okay? Not viscous boundary layer. And this big delta T is the temperature, is the relative temperature of the heat source. I just would like to point out that this theory is valid for very small variation of temperature. Otherwise, we will get viscosity and the density and the specific heat would depend on temperature. Okay, so in this case, for example, kinematic viscosity, density, and the specific heat, they are constant. Now, I can substitute these quantities here into the temperature equation, and I can get the temperature equation expressed in non-dimensional form, okay, which is specified here. Now, the second and the term on the right-hand side are much smaller than the first, okay? So that means that the temperature for these scales, for these two scales and the scales that I introduced at the beginning, the temperature does not depend on the fast time oscillations, okay? Because this term would be equal to 0, okay? So that means that we can assume T, the temperature, as a slowly varying function of time, okay? Depends slowly on time. So if I assume this, I can integrate, I can average the equation with respect to the fast time, and I can get this equation here for the temperature. As you can see, there are no velocity components depending on time. So U1 and W1 are not present here. Okay, U1 and W1, if you remember, are the leading order velocity components. They don't appear here anymore. Okay, this equation here is much simpler than the previous one because of this, because U2 and W2 just depends on space. Okay, and this is expressed in physical variables. You must think T here as a slow time scale. Okay. PR here is the Planck number, is more or less equal to 7 for seawater. Unfortunately, U2 and W2, they have a very complicated spatial dependence. So the analytical solution can be still challenging. So this equation must be simplified, okay? Now, let's consider just propagating waves. So the case in which R, so the reflection coefficient, is equal to 0. The blue curve shown here is the Eulerian mean horizontal component, which, as you can see, it looks quite complicated. So it grows linearly, then it starts to oscillate and reach a constant value. Well, analytical solution in presence of this velocity component is quite difficult. So let's try to understand what's going to happen if I consider approximated velocity. For example, I can consider a constant velocity here, so which is represented by this red line. So basically a uniform flow, okay, constant velocity. And then I can consider the trapezoidal approximation here, so the yellow curve here, so in which the velocity increases linearly, and then it reaches a constant value when z is equal to 3 delta divided by 2, where delta is the viscous boundary layer thickness. And here you can see the expression for the trapezoidal velocity component and the expression for the uniform flow. Let's study the uniform velocity, the case for the uniform velocity profile, which is basically similar to the problem that I already showed you, right? So except for the fact that there is no time dependence in the velocity component here. So solution can be found on the same way. And now the integral can be solved explicitly. And the solution is given here. So temperature is a composition of these 4 terms. So the first term here is the steady state solution. Does not depend on time. The second and the third, and the terms on the second and third row represents the time dependence above and outside the heat source. When time increases at very, very last time, this term, so the Heaviside function, it can be written, it becomes equal to 0. So this term does not exist anymore. And the solution at very last time, so the steady state solution, is given here. So in which Rc is the complementary error function. So let's try to estimate the thickness for the thermal boundary layer by using this expression here. If I consider just the thermal boundary layer above the heat source, I can define the boundary layer thickness as the thickness for which the temperature is 1% of the heat source temperature delta T. So a similar definition as in the case of viscous boundary layer. But in that case, we refer to the velocity clearly. Now, if I assume this, I can find this expression here. So delta T is equal to this quantity. Now, if I assume these values for sea depth, h, so sea depth about 10 meters, with amplitude of 1 meter, frequency of order of magnitude of 1 radian per second, I obtain that delta T has an order of magnitude of few centimeters. So it can be much larger than the viscous boundary layer. Okay? And this is indeed shown here. So for example, here, the thickness is about a couple of centimeters, but the viscous boundary layer can be much smaller, maybe a few millimeters. I can approximate this expression in shallow water and deep waters. So when kh is much smaller than 1 and kh is much larger than 1. And from here, this is the ratio between the thickness of the thermal boundary layer and the thickness of the viscous boundary layer. As you can see, the thickness in deep waters is much larger than in the case of shallow waters. That's simply because the velocity field at the seabed is much smaller. Okay? And also you can note that the growth of the thermal boundary layers is expressed in this form. So it grows accordingly the square root of x. Okay? And this is also shown here. So I show you here also, I can show you the effects of different frequencies for fixed values of heat source temperature, heat source length of 5 meters, wave amplitude, fixed wave amplitude, and fixed sea depth. The figure A represents the case of frequency equal to 1 radian per second. Here, I consider a larger frequency of 1.5 radian per second. As you can see here on the right-hand side, the thickness tends to increase, just because when the larger the frequency, the smaller the wave velocity. Okay. Also, delta T is very rapid and slow down as x increases, because it grows accordingly the square root of x. And then the temperature decays for large x. Okay, so when x increases, the temperature tends to decay. So the thermal boundary layer is also characterized by an horizontal width. Okay, not just a vertical dimension. This horizontal width can be important when we consider multiple heat sources, because they can interact with each other. Okay? So how can we estimate the horizontal width of the thermal boundary layer? So we can try to find the location of the maximum of temperature for each value of x. Okay? Now, in the region, in the heat source region, the maximum of the temperature corresponds with the heat source itself. Okay? So the temperature is basically located in z equal to 0. Outside from the heat source, basically here, the maximum of the temperature, it tends to grow towards z. Okay, so the larger x, the larger is the z coordinate of the maximum. So how can we find this curve? So this curve is given here. So outside the heat source, this is the location of the maximum for the temperature. And here, you can see the value of the temperature, okay, for all the value of x. Okay? So the figure here shows the maximum value of the temperature outside the heat source. So when we are, and as you can see, for example, after this represents x minus L, so L represents the right edge of the heat source, okay? And this is the ratio between the maximum value of the temperature and the temperature of the heat source. So in correspondence of the right edge, this ratio is equal to 1, because we have the same temperature of the heat source. When we move towards larger value of x, the temperature tends to decrease. And for example, if we consider a heat source of width equal to 5 meters, like the example that I showed you before, where after 10 meters, the temperature is just 10% of the value of the heat source temperature. Okay? So this curve allows us to estimate, for example, the horizontal width of the thermal boundary layer thickness. But it's interesting to note that this value here does not depend on the fluid velocity. Okay? I would say, well, the velocity should increase the width of this thermal boundary layer, but apparently this is not the case. Okay? So the velocity only affects the vertical dimension of the thermal boundary layer thickness. So the horizontal width depends just on the length of the heat source. This is also shown here, right? So this is basically the horizontal dimension, approximately, which is the same dimension that we have here. But the vertical width is different. Maybe it's difficult to see here, but the vertical dimension is different, but the horizontal width is the same. Okay? We derived the temperature. Now we can derive the total heat flux. So we can apply the Fourier law here. So K is the thermal conductivity. The total heat flux is the integral of Q evaluated in correspondence of the heat source. So this is the total heat flux exchanged between the heat source and the ocean. So we basically derive the temperature, then integrate, and we can find these two values. So QSB is the heat flux exchanged between the heat source and the ocean in correspondence of the heat source. Q for x larger than L is the heat exchanged in this region, so outside the heat source. Okay. Now, as you can see here, it's negative, simply because in this case the heat flux is directed towards the seabed. The values, the magnitude, is the same. That's because the heat in the fluid domain remains constant in steady state, and this is a consequence of the first law of thermodynamics. Okay, so we have positive heat flux here and negative heat flux here. Here we don't have nothing, simply because the temperature is directed there, towards the right, bends towards the right. Now, this is the case for uniform velocity profile. What's going to happen when I assume the trapezoidal velocity profile, so a more realistic situation? Now, again, I recall the velocity components. Okay, so the derivative is not continuous. And I can write the boundary value problem here. So I assume a generical distribution of temperature at the seabed. Okay? And for simplicity, I consider the steady state. So what's going to happen at very large time? Now, the fluid domain has infinite extension with respect to x. So we can use the Fourier transform with respect to x and simplify this problem into this form. Now, remember that depends on z in this way, okay? So it's z until 3det divided by g. Then it remains constant. So this problem here can be solved by matching the velocity and the heat flux at this common boundary here. So where the velocity changes the stiffness. Okay, the velocity profile changes the stiffness. So the number 1 in the parentheses refers to the fluid domain between 0 and this coordinate. The number 2 in the parentheses refers to the fluid domain above 3 delta divided by 2. Now, this problem can be solved. Now, the first equation admits a solution expressed in terms of Airy functions, and the second equation can be written, the solution of the second boundary layer problem can be written in this form here. Now, there are these constants, C1, C2, and C3. That depends on the, again, on the Airy functions. They are very long, are known, but they are very long and are not reported here for breadth. But this is the solution where the velocity grows linearly, and this is the solution where the velocity remains constant. AI and DI are the Airy functions of first and second kind. We can again apply the Fourier law and get the heat flux at the seabed, so in correspondence of the heat source. And it can be expressed in this integral form. Now, again, for simplicity, I can consider a heat source of 5 meters length and characterized by constant temperature, and try to evaluate these two expressions. So I assume the heat source as previously, and I can get the following temperature field, which looks similar to the previous case. Okay. The only difference is that the temperature field bends towards the right more slowly. That's because in the region very close to the boundary layer, the velocity is increasing linearly. In the case of uniform flow, on the contrary, the velocity is basically constant from z equal to 0 to infinity. Okay, but anyway, the temperature field looks very similar to the previous case. The difference, it can be represented here. So this is the heat flux in a trapezoidal flow and uniform flow. So the difference is located here to the right-hand side of the edges. So maybe it is quite difficult to see, but the uniform profile case tends to exchange more heat than the case of trapezoidal velocity profile. Okay, and this clearly has consequences in total heat flux exchanges, as I will show you later. Then here you can see the velocity basically goes up to infinity, to plus infinity, and here to minus infinity, just because there is an instantaneous change of temperature at the seabed. Okay. Now, we analyzed the case of uniform and trapezoidal velocity profile in presence of heat sources characterized by constant temperature and fixed width. So what's going to happen if the heat source, for example, is different? For example, we can consider the case of Gaussian temperature distribution, okay, where the temperature varies accordingly this expression here. So again, we can apply the Fourier transform, and we can get the solution expressed in this integral form. Okay, and again, for simplicity, I can consider the case of uniform flow and the steady state case. So no time independence. This expression here allows us to find the heat flux by applying the Fourier transform. This integral can be written in terms of parabolic cylinder functions, d here. So we have an explicit expression for the heat flux at the seabed. Now again, let's try to represent this solution here, the temperature, and we can get this. Okay. So we have again the same parameters for free surface wave amplitude, wave frequency, 1 radian per second and 1.5 radian per second. we have this parameter beta that defines the width of the Gaussian temperature distribution. And the maximum of the temperature is equal to 10 degrees. But again, we have the same result. So the larger the frequency, the larger is the thermal boundary layer thickness. We can also represent the heat flux at the seabed here in z equal to 0, which is shown here for the two different frequency values. As you can see, there is a maximum and a minimum for the heat flux. Now, the maximum first is not located in correspondence of the maximum of the temperature, because the maximum of the temperature is located in x equal to 0. And there is also a minimum. Now, these values here can be found, for example, by trying to find the maximum and the minimum value for the previous expression, for this expression here. But this is complicated. So since these values are very close to 0, we can try to perform a Taylor series expansion about x equal to 0. And that Taylor series expansion gives us these two approximated values for the maximum and the minimum values of Q, which are very close to the maximum that we found. So the dashed line corresponds with x max and x minimum. Okay? And they are very close to the maximum of the function. Okay, now the problem of temperature can be, let's say, easily solved by applying numerical techniques. Okay? So for example, we can apply a Crank-Nicolson scheme. There are other schemes, but I'm not an expert, so I'm not an expert of numerical methods, so I simply applied a Crank-Nicolson scheme, and I tried to solve the complete problem. Okay, so the problem of the complicated spatial dependence of the Eulerian mean flow, and I tried to compare the case of uniform and trapezoidal velocity approximations. Now, here you can see the values of, again, heat source temperature, sea depth, and so on, for two different values of heat source lengths. So the figure on the left represents the case of L equal to 2.5 meters. The figure on the right, the length is equal to 5 meters. As you can see, the trapezoidal approximation is very close to the full numerical solution. Okay? On the contrary, the case of uniform flow, it tends to overestimate the heat exchange rate. That's because in z equal to 0, the velocity should be equal to 0, right? But the uniform flow does not consider that. Uniform flow, it considers basically that the velocity is constant throughout the depth. So we can say that the uniform approximation is valid only at very large frequencies, where the velocity of the free surface related with free surface waves is not very large. On the contrary, the trapezoidal approximation is very accurate. This is also shown here. So for example, I consider the Gaussian temperature distribution. And again, the uniform flow tends to overestimate the heat flux, Q. And the trapezoidal approximation is very close to the full numerical solution. Okay? This is the solution for these quantities. So beta equal to 1 meter to minus 2, and the usual quantities. Okay, we analyze the case of simple propagating waves. What's going to happen when I consider the case of standing waves? Okay, when r is equal to 1. When r is equal to 1, the velocity field in the viscous boundary layer is more complicated. And here, for example, you can see a schematic variation of the mass transfer velocity beneath the standing waves. So you should imagine that here there is a breakwater. Okay? So solution of the temperature equation in presence of these velocity components is very complicated. Okay? So for the moment, I simply solved this case by applying the Crank-Nicolson scheme. Now, the velocity components, they have this pi divided by k horizontal periodicity. Okay? From you see there is some repetition here. So here you should imagine that there is the node of the standing waves, and here there is the antinode of standing waves patterns. Okay? But pi over 2, pi, and so on, there represents some switching points for the horizontal velocity component. So in other words, two different heat sources symmetrically located with respect to these velocity switch points. For example, if I consider a heat source located here, so between 0 and pi over 2, and a heat source located between pi over 2 and pi, they will promote a symmetric temperature fit, but the same total heat flux. So we can get basically a complete picture by just considering cases in which a heat source is located between 0 and pi over 2, or the center of a heat source is located between 0 and pi over 2. Now, we can define this non-dimensional heat flux. This, the width of the heat source expressed in non-dimensional form. This is the location of the heat source. And x0 prime is the non-dimensional horizontal distance to the center of SB. SB denotes the location of the heat source. So when x0 is equal to 0, we are beneath the antinode. When x0 is equal to pi over 2, we are here, basically, beneath the node. Okay? And this is the behavior of heat flux versus heat source length. As you can see, when the length of the heat source is very, very small, okay, much smaller than pi over 2, you can see that the location that maximizes the heat flux is equal to x0 prime equal to pi divided by 4. So in other words, when the heat source is located here, so between 0 and pi over 2, we have the maximum of heat exchanged. And in this region, the horizontal component of the Eulerian mean flow is maximized. Then when the heat source length increases, there is no effect on the location anymore, because everything is basically averaged. Also, you can see that maxima and minima appears with this periodicity equal to pi over 2, and this is due to the periodic inversion of the velocity components. Okay, so there are some bumps here.
Sorry, we need to maybe wrap up in 1 or 2.
Yes, yeah, this is basically the same slides. So I have just 2 slides left. So this curve here represents the ratio between the 2 different heat flux. If I fix the heat source in the, basically this is the heat flux exchanged between a heat source as if it was placed in the open ocean in presence of simple propagating waves, and the heat flux if this heat source is located in front of a breakwater. As you can see, the effect of the breakwater is important when the heat flux, when the heat source length is very large. When the heat source is very small, it tends to exchange more heat if it is placed in the open ocean. I think this is due to the fact that here there are recirculating cells that tends to increase the thickness of the boundary layer. Okay, so the total heat flux is smaller. And finally, here, sorry if I'm okay, so sorry, there is also, so from this curve here, you can also see that this implies that a heat source placed in front of a reflecting structure exchanges more heat, provided L is larger than approximately L prime larger than pi to 4, where L prime is the non-dimensional heat source length. Finally, here you can see what's going to happen in the case of standing waves. So for example, this is a heat source located beneath the antinode. So here I have the velocity component directed upwards. So this orange arrow represents the schematic variation of the velocity component. This is the heat source located in correspondence of pi divided by 4, where the horizontal component is maximized. Here there is no temperature because I neglected horizontal diffusion. Okay, and there is no horizontal component of the velocity. And here, this is the case in which the heat source is located beneath the other antinode, where the velocity is directed downwards. Okay, this presentation is related with these two works. One is published on JFM, another one is simply accepted, and this has been done in collaboration with Raphael Stuhlmeier and Professor Bortwig from Plymouth and Conrad Kremer from Oxford and Delft. Thank you.
Brilliant. Yeah, we maybe got time for a very quick question, but we can also go for a coffee in the staff room after, so you're welcome to ask any questions there, but I don't have anything pressing now. So yeah, just quickly, I was going to ask, like, what would your advice be to these people who are trying to use the sea as a kind of sink to use in their kind of heat exchangers? Is this work able to like inform the design of those things too?
Well, this is a first step. It's not. I think that here we need to combine even the turbulence effect. So this is the very first step towards the understanding of behavior of the temperature field. Yes. Currently, I'm exploring the effects of the presence of turbulence effect with two postdocs in Plymouth, but that is a completely different words to this case. And for example, here we can see basically what's the effect of free surface waves, because sometimes it is neglected. So if you will accelerate it exchange it in absence of well, if there are other waves here, you can see what's the effect, what's going to happen.
Quick question, or
yeah, good, very quick.
So in the solution that you showed with the approximation, both shallow and deep waters.
Yeah. You mean the boundary layer?
For the boundary layer, yes. I'd assume that for deep water. Yes. So why is it e to the power kh? Why is it e to the power kh?
No, I mean in shallow water.
No, it's in deep water. In deep water.
Yes.
Right. So in deep water, I'd assume that it would go to a constant, right? So right now it looks like it's exponentially growing.
Yeah, exactly. It grows a lot because when I go in deep waters, so basically it's like that the velocity tends to be absent, and basically the increase of the boundary layer thickness it will go basically towards infinity.
So that's
unrealistic.
Okay, I see. Yeah.
So I simply basically when kh is very large, I simply substitute the behavior of the hyperbolic sign, because the behavior of the hyperbolic sign for very large values of kh is that it behaves accordingly to this exponential function.
Okay.
So yeah, let's say that the theory wouldn't be valid anymore because the thickness would be too large.
Okay, excellent. Thanks, Simone, again.